Alright guys, as we return to our final section of Chapter 5, I want to sincerely apologize if there's a background noise disturbing you. They are doing some road work out there. Alright, our last section of Chapter 5, we're going to continue our work on annuities by looking at present value versus future value and talk about amortization. When you pay off, for example, a mortgage, you get an amortization table, and it shows you how much of each payment is applied to interest and how much of each payment is applied to principal. Now, on review, last section we talked about annuities where regular deposits are made so that the value of the annuity increased from zero at the beginning to some future value at the end. So we are looking at investing and seeing how much money is accumulated at the end of the term of the investment. Now we're going to focus and talk about finding the present value instead of finding the future value. Sometimes annuities begin with money, make regular payments out each period until the balance decreases to zero. So we're going the other direction. I mentioned earlier like an insurance settlement paying out. Other examples would be a lottery jackpot that has structured payments, structured settlements, like that insurance payout that we discussed, or maybe a court settlement, and things like trust funds where you have a total balance at the beginning and you are receiving regular payments instead of making regular payments. Now if you look at your formula sheet for ordinary and annuities due, we have so far focused on finding the future value. Now we're going to focus on finding the present value. How much do we need now to be able to make all those payments without running out of money until the end? Okay, present value of an annuity, the amount that has to be deposited today to provide all the payments for the term of the annuity. It doesn't matter whether the amount needed is to accumulate funds or disperse funds. How much do we need to put in today so that we have it as what we need at the end of whatever time? If we're looking for ordinary annuities, this is our formula. Let's think about how it differs from our previous formula. In fact, I'm going to pull our formula sheet back out. When we were solving for future value, we did this calculation with the exponential and then subtracted 1. When we're solving for present value, we turn that around and we have 1 minus this calculation, and notice that my exponent is now a negative exponent. So this top part, this numerator inside my brackets, gets just a little bit more complex only because we have to make sure we do order with subtraction, 1 minus this value, and that we make sure that we have our exponent negative. Okay, so here we go. Nothing else has changed. I is still R over M. N is still my total number of payments, and N is still M times T. So all of those pieces of information that are part of the formula are the same. Okay, here we go. Camilla was in an auto accident. She sued the person at fault and was awarded a structured settlement in which an insurance company is going to pay her $2,000 at the end of each month. At the end of the term, that means it's an ordinary annuity for the next 7 years. 7 years, there's my value T. How much money should the insurance company invest now at 4.7% compounded monthly to guarantee that all the payments can be made? So notice that I'm marking things as I read so that I know what I have. How much should the insurance company invest now? That's present value. So we're trying to find present value. Okay, so our present value formula for an ordinary annuity, payment times, and then inside my brackets, I have 1 minus, and then inside parentheses, 1 plus I to the negative n power. So I need to calculate I need to calculate n. I is going to be rate over M, my compounding period. So rate becomes 0.047 compounded monthly. N is that compounding period times the number of years. So 7 times 12 comes out to be 84. When I plug in what I know, she's going to get $2,000 a month payments. I is my denominator. In my numerator, I start with 1 minus because we are calculating present value, not future value. In parentheses, 1 plus that value I, and that is raised to the negative n power, so negative 84 for this problem. Okay, so let's figure out how much the insurance company has to set aside now at 4.7% to make sure that those payments are going to be available for Camilla. I'm going to start inside my parentheses here in my numerator, 0.047 divided by 12. I add 1 to that, and that gets raised to the negative 84 power. So my exponent button, by now, hopefully you remember this negative button is down here. It's not the same thing as subtraction. So negative 84 is my exponent. And this is the amount I need to subtract from 1 in my numerator. Subtraction order matters. So I have to start with 1 minus. So 1 minus, and then I didn't write down that number. It's not a problem. I use that second answer function, and it brings it back for me, does all the work for me. That's my numerator. Now I need to do the division. That's all of this in the numerator. Let's divide by my denominator. We're going to stick in parentheses. So that's the value of the brackets. It needs to be multiplied times the payment amount. All right, this is the amount the insurance company needs to invest to fund those withdrawals over 7 years. So we've got $142,924.79. That's how much they have to invest now so that she can get those $2,000 a month payments for 7 years. All right, let's look at the next page. To supplement his pension, Hong plans to use $400,000 of his savings as an ordinary annuity that will make monthly payments to him for 20 years. If the interest rate is 5.2%, how much will each payment be? So here's my how much statement. I'm going to be solving for payment this time. Now, this $400,000, this is what he has now to invest. So this is the present value, which means we're going to be using our present value formula for ordinary annuities, monthly payments, that's my value for M, 20 years, that's my value for T, and then there's my rate. Well, my value I is the rate per payment compounding period, so 0.052 over 12. N is going to be the time times the compounding period, so 12 times 20. So N is going to be 240. But remember, since we're finding that present value, we're using our present value formula for an ordinary annuity, that we're going to use that exponent as a negative value of N. Now, we're going to be solving for payment. We know present value. To solve for payment here, instead of multiplying by this amount, we're going to divide by that amount. So I'm going to go ahead and move this chunk over so that I have payment is equal to present value divided by all of this. So I'm solving for payment. That's going to be equal to the present value. He's got $400,000 divided by, and looking back at that chunk in brackets, that's what goes in my denominator. So I is 0.052 over 12. My numerator is 1 minus, and then in parentheses 1 plus I to the negative N exponent. And that's going to give me my payment value. Okay, starting in parentheses, 0.052 divided by 12 plus 1. And then I'm going to raise that to that exponent. exponent negative 240. This is what I need to subtract from 1. 1 minus this value. So 1 minus, bring back that second answer. And this needs to be divided by I. So this divided by, and then in parentheses, I. That's my denominator. That's down here. So I've got 400,000 divided by this amount. Still not rounding off. Order matters. 400,000 divided by, and then I bring back that second answer calculation that's living in my calculator waiting on me. That's how much the monthly payment will be. I'm going to round that to 22 cents. So Hong will be able to withdraw $2,684.22 a month for 20 years if he invests that $400,000 at a guaranteed rate of 5.2%. All right, loan amortization. So here we go. The bank looks at the repayment of major loans, like a car or a house loan, as an annuity. That has you paying the bank a fixed amount each month. A fixed amount each month. In this case, when we talk about PV or present value, that's the principal, which is the amount you borrow. So when I teach loan payment values, loan amortization in other classes, we don't use PV, we just use P for principal. So to calculate your payment of your loan, it's just like that present value formula that we've been working with. So to find the payment, we do PV over, and this is exactly what we just did. We rearranged our formula. That's all we did. Okay, in order to purchase a home, a family borrows $184,000. So that's the present value. That's their principal, how much they borrowed. 3.2% is my rate. 30 years is time. Monthly payment, so M is 12. And we're going to round the answer to the nearest cent because it's money. So if we need I and we need N, I is going to be rate as a decimal over our compounding period, monthly payments for loans like car loans and house loans. N is that compounding period times the number of years. So over 30 years, we're making 360 payments. Now this is assuming we pay it off as scheduled. If you pay something off early, you save so much interest. In fact, we are cutting 13 years off our 30-year mortgage by paying about $500 extra a month on our house payment, saving us hundreds of thousands of dollars in interest. So it's always good to pay things off early, but we're assuming with these problems that we're paying things off as scheduled. So here's my formula right here up above, so I'm not going to rewrite it. I'm just going to plug in values. My present value, or my principal, is the amount they need to borrow for the house. In my denominator, I have that set of brackets. The little denominator in here is I. Above that, I have 1 minus, and then in parentheses 1 plus I to the negative n power. You know what? I just noticed that they simplified our formula for us, didn't they? If you divide by a fraction, how do you divide by a fraction? Well, you multiply by the reciprocal. When you multiply by the reciprocal, For example, if this is my fraction I'm dividing by, when I multiply it, that flips upside down and that I goes up into the numerator. So this is the simplified version. If we want to use that simplified version now, we absolutely can. You can do it like this, or you could say 184,000 times this I, and then this part is all that is in my denominator. And this is actually the version of the formula that I usually work with in my other class. When I do this, I'm still going to start with my denominator and I'm going to work. Well, we can start with our numerator. Let's do that. Let's do 0.032 divided by 12. Gets me that decimal. I'm going to multiply that times my present value. We borrowed 184,000 for the house. That's my numerator, 490.6 repeated. So my numerator is going to be 490.6 repeated. And when I come back, so that I don't mess things up by rounding, I'm just going to put in a whole bunch of sixes for that numerator. Now I need to figure out what that denominator value is going to be. So let's do that. There we go. 0.032 divided by 12. Add the 1. Raise that to the negative 360 power. Subtract that from 1. So 1 minus that second answer. That is my denominator that I'm missing here. So I need to take my numerator and divide it by this value. My numerator is 490 point lots of sixes divided by second answer. Bring that back up that we calculated. There's my monthly house payment. Well, principal and interest part of the house payment. That does not include taxes and insurance. So let's just say that we pay this house off as scheduled. We pay this house off as scheduled. What total principal and interest will we end up paying if we pay this house off as scheduled? Well, we're going to be making that payment $795.74. That's our payment. We would make it 360 times because we're making monthly payments over 30 years. So if I take that payment, $795.74, 360 times, the principal and interest is going to be $286,466.40. Now we just borrowed $184,000, so if I subtract that principal out, it shows you that the interest I would have to pay on our $184,000 house loan comes out to be over $100,000 over 30 years. So again, definitely worth it to pay things off early. Okay, last page for this section. In October 2016, the average rate for a 30-year fixed rate mortgage was 3.37%. I'm going to assume that a down payment of 20% is required on a home purchase of $285,000. What does that mean? If we're paying a down payment, that means we're paying money up front. So if this is the home purchase price, I'm going to have to pony up 20% of that now, and that amount is being paid off, so it's not being financed. So I need to find 20% of $285,000 to see what my down payment would be. So that would be a down payment of $57,000. If I'm paying $57,000 down now, I'm not having to borrow $285,000. How much is actually being financed? Well, I'm going to take that $285,000, subtract the down payment, because I just paid that part. This is how much I need to finance, $228,000. So that's how much I'm financing. That's my principal, or my present value, for my monthly payment calculation. All right, we're going to amortize that loan by finding our monthly payment. We're borrowing $228,000, so that's my present value. My rate over 12 because I'm making monthly payments. It's a 30-year loan, so I'm making 360 payments. If we calculate our numerator, my numerator is $640.30. $640.30. My denominator I need to work out. This is what I subtract from 1, so 1 minus that answer. That's my denominator. And I have numerator divided by denominator, so 640.3 divided by that second answer. That would be my monthly payment. Round it to the nearest penny. So my monthly payment for this house is $1,007.35. We're going to assume the loan is paid off as scheduled. If it's paid off as scheduled, after 10 years, about how much is left on the loan? Well, the question we need to first ask ourselves is how many payments are left? How many payments are left? After 10 years, I've made monthly payments for 10 years. So that means there's 20 years left on my loan, right? It was a 30-year loan. I've paid for 10. There's 20 years left on my loan. So 20 years of monthly payments means there's 240 payments left. We're going to use our remaining balance formula. Now this is going to approximate. It's not going to give it just perfectly exactly to the nearest penny. It's going to approximate it. The remaining balance after X payments. So after X payments, X is the number of payments that we have made. That means N minus X is the number of payments left. That's my number of payments left. So I have 240 payments left. That's still a negative exponent. So the balance remaining, I'm going to take my payment, well, we calculated our payment, times, and then inside parentheses, 1 minus 1 plus I. Well, we're using the same value for this particular loan. This exponent is now a negative 240 because that's how many payments are left, over I. And we've shown this calculation several times now, so you know how to work it out in your calculator. The balance remaining on the house is $175,710.23. That's how much is still owed. So, how much did we borrow? Well, we borrowed $228,000. This is how much we still owed. How much has been paid off? Well, if I subtract $228,000, that was my principal that I borrowed, $228,000 minus the amount that's still due, I see that we've only paid off $52,289.77. Why is that not much? Why do we still owe so much of our loan? And that's all that we've paid off of the loan balance. Well, the reason is, at the beginning of your loan, almost everything goes to interest. Let's look at our amortization schedule. We're going to calculate just those first 3 payments and how it's applied to the loan. So we borrowed, so our loan balance that we borrowed was $228,000, right? We make one payment, and we can use our simple interest formula to determine how much of that payment goes to interest. PRT. And simple interest is interest equals principal times rate times time. So our principal was the amount we borrowed. Our rate was the 0.0337%, and our time is 1 month. Remember, this is always annual unless we're told differently, so it's a 1/12 of a year. So for my first payment, I'm paying interest on the full amount we borrowed for 1 month. If you plug that into your calculator, you figure out that that's $640.30 interest. So out of my first payment, $640.30 goes to interest. You might recognize that amount as our numerator up there. Ta-da! This goes to interest. Well, if that much goes to interest, how much goes to principal? I would take my payment. My payment was $1,007.35. Subtract the amount that went to interest, and the rest of it was applied to the principal of my loan. So this paid off a little piece of the loan, $367 worth of the loan. So I'm going to take my loan balance, $228,000, subtract $367.05. That means now, after that first payment, I owe $227,632.95 because this was paid off of my original balance. All right, the next payment, my second payment. To calculate how much of it goes to interest. Same calculation, except that I've paid off a little bit. So this is now my principal. The rate is still the same, and it's 1 month of payment, 1 month of interest, so the time is 1/12. When I calculate this, I see that for my second payment, $639.27. So about $1 less goes to interest on the second payment, which means about $1 more goes to principal. So I'll take my payment amount, the $1,007.35. So my payment is $1,007.35, and it is split between these two columns. This is how much went to principal, so the rest of that amount went to interest. No, I said that backwards. This is how much went to interest, so the rest of that went to principal, about $1 more. This gets subtracted from my loan balance. So now my new loan balance at the end of that second month, still over $227,000. I only paid $1 more of interest out of that second payment. What about the third payment? Let's see how we do there. Well, on our third payment, interest equals PRT. My principal is now $227,264.87. Rate is the same, and it's 1 month, so 1 out of 12, 1/12 of a year. When I multiply that through, I see that this third payment, $638.24, goes to interest, so about $1 less again goes to interest. Out of the same monthly payment, sorry guys, I made that really sloppy, $638.24, out of the same monthly payment, so the difference between my monthly payment and interest gets applied to the principal. Oh, shoot, I copied down the wrong value here. I'm sorry, I bet I confused some of you. That should have been $368.08. I was looking at the wrong line on my key that I work from. This time we're at $369.11 that goes to principal, and when I subtract that from my balance that I had, I've got now $226,895.76. So each successive payment, I'm putting just a little bit more toward principal, just a little bit more toward principal. So if you put a whole, $200 straight to principal, that's going to count that loan balance down extra every month, and means that next month you pay a little less interest.